Okay, going into totipotency, you already have some idea, no? When we met in the live classes, I gave you a general idea of what it meant. So let us look at it in detail, okay? I just gave you the introduction. There is so much more that you don't know, okay? So you know that totipotency is the potential that is there in the genes of a cell to produce a completely new plan, okay? I'll repeat. There is something in the genes, okay? There's a potential in the genes that can make any cell regenerate into a complete plant, okay? So in other words, there is some character, okay, which has the potential to form a new cell type in the adult organism, okay? Means it can form all the types of the cells in the, how do I say? It can form any cell type, okay? In one cell, okay? In one cell, in its DNA, it has all the information to produce any type of cell, whether it's a root cell, a shoot cell, to generate the complete individual, okay? If just from one cell you take, everything is already there, the information, okay? So let's see how to express it in the culture. So plant tissue culture is when you grow a number of cells in the sterile condition inside the lab, okay, in a controlled environment. Okay, so these cells, you can get them from any part, and then you grow them in a medium which has vitamins, minerals, etc., hormones and all, and you allow the cells to divide and grow, okay? Then it will produce a callus, okay? A callus, as I told you, is an unorganized, proliferated mass of cells, okay? Those very highly divided mass of cells, okay? And they don't have any differentiation yet. They are not organized yet, okay? Then the cells of the callus, those are the totipotent ones, okay? So thus a callus tissue is totipotent, okay, because it can regenerate back to the normal plant after you manipulate the medium, okay? As I told you, if you want the root, you add auxin, shoot, you add cytokinin, okay? So Skoog and Miller, in the scientists of the USA in the 1950s, they discovered a new plant growth hormone which is known as kinetin from the herring sperm DNA, okay, from this fish. Okay, so they found a new plant growth hormone known as kinetin. Okay, I've already read last year, I think, kinetin. So if you concentrate your auxin and your cytokinin properly in a culture, tobacco culture, they could show the role of kinetin in creating organs, okay, organogenesis. When the ratio of kinetin to auxin was higher, only shoot developed, okay, known as calogenesis. And when the ratio of kinetin was lower to auxin, only root was formed, known as rhizogenesis. So to form roots is rhizogenesis, form shoot, calogenesis. That you know from the previous notes. Okay, so you can see how kinetin, this new hormone, it affected. Although the auxin was there, there's no cytokinin. There was auxin, but after they added kinetin, okay, they saw only shoot, and vice versa. Okay, then let's continue. Then Stewart at Cornell University, US, he grew carrot tissues, okay, by removing a small disc from the phloem region of the carrot root, okay, and he placed it in a moving liquid in the aseptic condition, in the lab condition, okay. With the presence of coconut milk in the medium, the phloem tissue began to grow actively. In the moving liquid medium, single cells and small group of cells, they were loosened from the surface of the growing tissue, okay. So in a liquid medium, no, everything is free, okay? It can move in, no? Like you can move in nicely like a fish. So when you take out those cells which had separated from the growing tissue and you grew them separately, it was found that some single cells developed somatic embryos, okay, or embryotes. Embryogenesis we learn, no? By process that is in the like the normal zygote embryo, okay? So he accidentally he was able to create embryogenesis just by suspending those callus in those the liquid medium, okay? So some experiments also they show that you can get xylem, you can get phloem, okay, without producing plant organ or embryos. You can get whatever tissue you want, okay. So if you produce a tissue like a xylem or a phloem, production of tissue is known as histogenesis or cytodifferentiation. So you can manipulate the cells, okay, to get what you want. You want an embryo or a tissue, okay, or a plant or a callus. You can manipulate. So how far these totipotent cells can behave depends on the microenvironment, means environment inside the test tube, okay. So if you want it to last for a long time, you'll have to resubculture. Resubculture means, okay, in this tube, no, in this test tube, okay, you added the media, the callus is here, then you added the vitamins, the minerals, nutrients, no. Then after 1 month, just example, the nutrients they have depleted, okay. Then again you take out one callus, then you add it into a new test tube. Then again you add your hormones, your vitamins, your minerals, etc. Then again this one gets depleted, again you culture it into a new test tube. So this is what is subculturing, okay. So I hope you understand what it means by subculturing, okay. Where were we? Okay, subculturing is done. Then you can observe that X plant first forms the callus tissue. Okay, let me read again. I'm tired. You can observe that the X plant will first, we will get the callus first, okay, from whatever tissue you brought, we'll get the callus first, okay. And then if you want to maintain the callus, you have to subculture in the appropriate microenvironment, okay. Then if you want to regenerate, you have to again change, you have to standardize. Standardize means you have to change the environment bit by bit, okay. So you have maintained your subculture with a callus, okay. You knew I add 1 mole of sugar, 0.01 mole of vitamin, okay, so on and so forth, I'll get callus. Then you start changing, okay, you change the ratio. You add more auxin, less cytokinin, or you add kinetin, like that, no? So you have to standardize, you have to keep changing to get your desired product, okay. So if you get a suitable medium, these totipotent cells, they will give rise to nodules or mesostomoids by repeated cell division, okay. So after you get these root nodules, meristematic nodules, no, meristematic cells are those cells which have the capacity to divide, okay, right, your root apical meristem, shoot apical meristem, I think you must have learned those, okay. So they may lead to vascular differentiation. Vascular differentiation means phloem and xylem, no, and you can form the root primordium or the shoot primordium, okay, which will give rise to the root or shoot, okay. So first you are getting callus, okay, then you are getting meristematic cells, okay, then from this meristem you are getting root, okay, shoot or root primordium, okay. Primordium is the first root or first shoot, okay. Then you can also, sometimes you can observe that those totipotent cells, they are giving you embryoids. No, remember that heart-shaped embryo, torpedo-shaped embryo. No, you've already excised it. No, with Miss CM. Okay. Then next. Then if you keep on subculturing, no, you will see that the callus, they become habituated. Okay, means they cannot grow anymore on the standard maintenance medium. Okay, they become habituated, and means habituated means even if you don't add the hormones, they know what to do. They've already figured out, I think I'm being force fed kinetin and auxin. I'm not going to observe it. I know that I should be growing right now. I should not be a callus anymore. Okay, so they'll become habituated, so you do not need to add those hormones anymore. They will by themselves regenerate into a plant. Okay, so subculturing for a long period of time also is pointless. Okay, so from a totipotent cell, it'll undergo differentiation, and you may get organs or embryo or tissues. Okay, then from the embryogenesis you'll get embryoid, then plantlet. Then from the organ you may get shoots, roots. Then this is what was this again? Shoot with root. Yeah, shoot with root. Okay, then from here the tissues, you will get the xylem, phloem and other tissues. Okay, so there is a crown gall. It's a disease. Okay, that affects plant in like the root. No, the not the root, the part where the root and the stem meet. There is like a tumor. Okay, like a tumor. Okay, it looks like a nodule, but it's not. It's like a tumor. And this disease, no, it has those cells which keep on growing. Okay, they keep growing. No. So that is your crown gall disease. Okay, you can Google by yourself. Okay. So here, the crown gall, it does not know to differentiate. Okay, it will just keep on dividing, becoming a tumor, because it has lost the information from the genes. It doesn't know that, hey, you are not supposed to keep dividing. You are supposed to become a root or a shoot or a cell, or a leaf. Okay, just like your cancer cells, no, they just keep on growing because that is just the keep on undergoing the cell differentiation. They do not know that they should become a neck or a arm. Okay, so this is how the tumor also behaves. Okay, means they have lost the capacity to be totipotent. They have no idea. They're just differentiating. They're just waiting for information, but something is wrong with the cells, the DNA, that they are not getting the information. Okay, they're just waiting, and in that process they just keep growing and growing. Okay, so you can the crown gall bacterium, Agrobacterium tumefaciens, it will induce a tumor known as tetratomas. Okay. Okay, let's continue. The importance of plant tissue is suppose you have a very economical plant, okay, either medicinal property or ornamental property, etc. So you can utilize this nature of totipotency and regenerate your own plant. Okay, you don't have to keep going to the forest to collect. So you can also modify them genetically. No, you read by yourself. Okay, you can exploit them according to your requirement. If you need a lot of root, you just give lots of auxin. A lot of shoot, you give lots of kinetin, etc. So cellular totipotency. Okay, so cellular totipotency, it could you could get it in the lab, no? But there was some failure, okay, to get the division, to get the cells to divide, okay. So these scientists, they cultured the root, and they could solve these problems of cellular divisions. Okay, so let's look at the main aspects. The main aspect is multiplication of a single cell in vitro and development of a whole plant from the proliferated tissues of this cell. Okay, so easy. You from one cell you get a callus, many cells, and this is step number one. And aspect number two is you get the whole plant from that callus. Okay. So there are some terms also known as de-differentiation. Okay, where the mature cell will go back to its meristematic cell. Okay, so once this cell, okay, first it was meristematic, no, the shoot or root meristem, then it formed the shoot, okay, the shoots, then it stopped behaving meristematically, no, but what if from an already mature cell, let's say this is the shoot, you could create it back into its differentiated part, and then from here, from this shoot cell, you got the root, you got the branch, you get the flower, you got it? So you can redifferentiate it. Okay, so this is a de-differentiated. So the ability of a component cell means a already matured cell, okay, already, which has already crossed the meristematic stage, to go back into its callus stage and come back into a whole plant, get regenerated back into its, what to say, into its clone, is known as redifferentiation. Okay. So you go through by yourself the difference between redifferentiation and de-differentiation. So this is the diagram. This one we have already done in this organogenesis or something, no, another chapter. So you can use the same diagram, okay, because this is nothing but totipotency only. So you can use the same diagram.